Hello, everyone, and welcome to ESEM 2022, to the third day of our virtual conference. I'm Marcelo Cataldo, and I'll be chairing the session on technical debt. We have 4 very interesting papers, and just a reminder to the authors, the presentation of research and industry track papers can be up to 10 minutes, and then we will have 5 minutes for questions. Then we also have 2 papers from the emerging results and vision track, and we will have 7 minutes to present those papers, and then 3 minutes for questions. For everyone watching these presentations, please put in your questions on the comments in YouTube and Facebook, and I will be selecting those questions, and the authors will be answering. So we will start with the first paper being presented by Cecilia Apa, a taste of the software industry perception of technical debt and its management in Uruguay. Cecilia, the floor is yours.
Thank you, Marcelo, for the presentation. Okay, my name is Cecilia Apa, and I'm from Universidad de la República in Uruguay. So this article was written in collaboration with Martin Solari from Universidad Hort Uruguay, Vallespir from Universidad de la República in Uruguay, and Guilherme Travassos from Universidade Federal do Rio de Janeiro in Brazil. So all authors are part of the Uruguayan engineering program, and this investigation was conducted within the framework of this program to collaborate with the Uruguayan software industry through evidence-based software engineering research. So I'd like to start talking about the background of this study. So what is technical debt? Well, technical debt is a relatively new concept. In fact, it is a metaphor that was introduced for the first time by Ward Cunningham. And he wanted to communicate to the non-technical stakeholders which are the consequences of delivering poor quality software in order to accelerate the software process. So delivering poor quality software is like going into debt. So, and this debt increases over the time with interests if you don't pay it. So from that first definition, many other definitions have emerged over the years from the scientific and industrial communities. So, however, there's no common consensus, neither by industry nor by academia, on what is and what is not technical debt nowadays. So, despite that, the scientific community has made a lot of effort in characterizing technical debt in several perspectives. Many secondary and even tertiary studies have been conducted in order to classify and organize the actual knowledge that we have about technical debt. Regarding the industry perspective, several investigations have also been done in the past few years, and the most used methods to explore this perspective were case studies, interviews, and surveys. The goal of these studies was to explore the understanding of the software professionals about technical debt and how their companies manage the technical debt in their projects. Well, until 2017, no studies had explored the industry perspective about technical debt in Brazil. So the experimental software engineering group decided to conduct a survey and asking to the software professionals if they were familiar with technical debt, and if so, what they understand by it, if their companies manage technical debt, and if so, which methods, practices, and tools they use to support it. So with the same goal, in 2019, we decided to replicate this study with the Uruguayan software practitioners. Well, regarding the survey design of this study, we have 2 research questions. The first one refers to if there's consensus in the perception of technical debt among Uruguayan software practitioners. Do they agree on what is and what is not technical debt? And the second one refers to, do the practitioners perceive technical debt in their projects? Do their companies manage technical debt? What management activities are most important to their projects, and which are the technologies that they use to support it? Well, we carried out our study between February and April of 2019 using an online questionnaire. We approached the software practitioners through different ways. The principal way was the mailing list of the Uruguayan Software Engineering Program, which has more than 500 members, and also through the newsletter of the Uruguayan IT Chamber, which concentrates most of the IT software companies, through the Uruguayan IT technical community, personal contacts, and social media. Well, regarding the results of the survey, we got a very high response rate if we consider that the population of Uruguay is about 3.5 million. So to this question, 150 participants, so a total, of 387 participants answered the survey, of which 259 gave us valid answers. To these participants, we asked if they knew what the term technical debt means. So to this question, 150 participants answered that they know, that answered yes. Well, these responses represents only the 60% of the total of valid answers. And to the participants who declare to be aware of the technical debt concept, we show them a list of software issues and ask them to select which items they think that can be related to technical debt. On the right, we can see the percentage of selected items by the participants. And we want to highlight that code smells, which is highly related to technical debt, was selected by less than half of the software practitioners. And a low internal quality, which is generally not related to technical debt and is not aligned with any technical debt definition, was selected by almost the same number of participants. Well, as a general result, and answering our first research question, we did not observe consensus among participants about what is related to technical debt. In fact, no item was selected by the total of participants that said to know the technical debt concept. Well, from the 150 people who declared to know technical debt, 126 declared that they perceived the technical debt in their projects. Of those, only 83 declared to manage technical debt. These 83 participants represents 66% of those who declared to perceive the technical debt in their projects and represents only 32% of the total of valid answers. Well, regarding the adoption of technical debt management activities, the most adopted activity are the technical debt identification, followed by payment and prioritization. The least adopted activities are technical debt measurement, followed by monitoring and documentation. Well, in some responses, the participants declared to perform technical debt payment, for example, but not perform technical debt identification, or perform technical debt prioritization, for example, without documentation. So we think that maybe the participants answer about the formal or systematic adoption of the activities. So in other words, maybe they identify technical debt, who knows how, and then pay it as a part of their formal assignment. Well, regarding the relevance given by the participants to each activity, the most important activities was the technical debt identification, which coincides with the most adopted activity, followed by prevention and measurement. And here we can see that the technical debt measurement and monitoring, which are the least adopted activities, are not necessarily perceived as the least important activities. So in fact, technical debt measurement was ranked as one of the 3 most important activities. Well, particularly for technical debt measurement, for example, 38% of the participants declared to perform this activity ad hoc. The most popular tools are Sonar Cube and Spot Bugs, or their previous version called Find Bugs. Well, comparing our results with the original study and with other related studies, we selected for this presentation a recent published work, the Inside TD project, which is a family of industry surveys about technical debt, and we shared some similar research questions. In the timeline, we can see the period in which each study was conducted. The orange bar is the original study, the gray bar is the Inside TD project, and the blue bar is our study. Well, regarding the awareness of the technical debt concept, All three studies have similar results. Around 60% of the respondents declared to know the technical debt concept. Regarding the perception of technical debt in their project, we cannot compare our results with the Insight TD because they don't have any questions regarding the perception. And if we compare our results with the original study, we can observe a higher level of perception in Uruguay, around 20%. And regarding technical debt management, we can see that the replication in Uruguay shows higher level of management than the original study, and both show a bigger difference than the Insight TD, almost double. But if we consider the percentage of management over the total of valid answers, we gave 32% of adoption, which is similar to Insight TD. Well, regarding the limitations and threats to validity, we believe that our biggest threat is the fact that the participants who declare to not be aware with the TD concept maybe were familiar with other concepts related to technical debt. For example, low internal quality or design erosion, among others. So it is likely that they perceive technical debt in the projects and maybe manage this debt, but with other names. Well, regarding the conclusions of the study, we think that the most important contributions to the industry are that there are indications that the technical debt concept is still unknown by a large part of the industry. So maybe further dissemination of the technical debt concept is needed. And there are also indications that the adoption of technical debt is still low and a large part of it is performed ad hoc. Also, although systematization of technical debt management activities reduce the capability of perceiving and managing technical debt in an opportunity manner. Well, for the researchers, the scientific community needs to provide more precise guidelines and instructions about how the technical debt management activities can be adopted in a better way. Also, we need further evaluation for the available technologies and tools that have been proposed in order to improve the adoption and support the performance of technical debt management activities. Well, it was important for us to give back to the software professionals, so we decided to spread the results of this investigation through different ways. An evidence briefing, meetings with software professionals, a talk in a software event, and a short video. Well, what's next? What are the next steps of this investigation? Well, there are questions that we want to answer. The first one is, why is technical debt management not adopted in a more systematic way? That is in order to get some insights about how to improve the adoption. And the second one is, what are the challenges and needs related to technical debt that the software industry are facing now? So to answer these questions, we are planning several focus groups with software practitioners. Well, thank you very much, and I'm open for questions.
Thank you, Cecilia, for the presentation. Thank you for staying on time. Please post your questions on the comments on both platforms. I'll start with one question while we get a question from the audience. I was wondering if you have any additional insights about the 42% of individuals that indicated that did not know or were not aware of technical debt in terms of demographics or distributions across industries, or some particularly interesting aspect that you may have.
Okay, that I really don't remember it in much, but I think that maybe the junior professionals, we asked the participants some questions to characterize the population. So maybe the junior participants ask the responses. The responses of the junior participants maybe are more that not be aware to the technical debt than, for example, the experienced participants or for example, the architectures participants. We also asked the participants what their role that they play in the software projects. So, for example, the software architectures are more aware of technical debt than, for example, the testers of the projects. So, but I don't have the numbers now in my head, but I remember that.
Perfect. Let me put another question here. So, thank you for the presentation. were you able to identify at what time or phase in the software development process practitioners resolve technical debt?
So the survey can not answer to that question because we don't ask to the participants what are the stages of the software project that they are in that moment. So I don't know what is that stages, but for example, we study about the software startups, and we can see that, for example, in the early phases of the software project, maybe if you are testing your idea, or you don't know what are for example, the next steps of the software process, the product that you are developing. Maybe you are not you don't worry about technical debt in that moment, and you start to worrying when you have the next steps of the software project, or how your product will evolve in the next steps. So if you are early in the early steps of the software project, you don't worry about technical debt, and the worry starts more in the next steps.
Good, thanks. And we have time for one more question. I think it's an interesting one from an education perspective. It is hard to understand the concept of technical debt, particularly when you are a junior student. And in an academic environment, you have small projects, and there may not necessarily be the
I know.
for that. So how do we go about starting teaching and developing those particular skills?
Well, it's an interesting answer because I have the same problem with the students. So maybe we can assign to the students some different works. For example, you don't need to do a task from the start to end, and then the task is over. So maybe we can assign to the students an evolving task. So maybe you need to develop some things and need to evolve this something over the assignment, and maybe with this they can perceive the technical debt when the product or the assignment are evolving. For example, you can change the requirements or change some of the specifications from the start. So maybe that will be a form or a way to teach about technical debt to the students.
Okay, perfect. Thank you very much for the presentation and the
Thank you.
And the answers. We now move to our second paper by Arthur Molnar. For those who are watching the program, there was a slightly shift of the order, but Arthur is here now to give the presentation of his paper on long-term evaluation of technical debt in open source software. Arthur, the floor is yours.
Okay, thank you so much. I hope that you can hear me, and I hope that you can also see the screen that I have with the title of the presentation. And so I'm here to present the results of our case study, where we examined how technical debt evolves over the long term in open source software. Okay? And we're going to start with a brief introduction to technical debt, how technical debt is measured using the latest tools, and kind of the related work. But in the context of related work, I'm going to talk about basically the strengths and the weaknesses of measuring technical debt using modern tooling, after which I'm going to present our case study. We go by presenting the research objective, the target applications, and also the way we've collected data and our most important results, after which I'm going to present our, let's say, most important conclusions. So let's start it. So first of all, the first mention of technical debt happened around 30 years ago. And I think that this first mention remains very consistent with what we see today. Now, later on, Martin Fowler described technical debt as basically taking in a quality deficiency in software knowingly, which would quicken development over the short term. So when we think of technical debt, we think of debt like in financial debt, which most people are more familiar with. So technical debt, just like its financial counterpart, has also a principal, and it also has an interest. So basically, the principle happens when we make a shortcut. Okay, we want to speed up development very quickly so something gets done by tomorrow. Okay, and usually what happens is that one suboptimal decision leads to another suboptimal decision, so on and so forth. And this compounds in the form of interest. And existing research has shown that this can spiral out of control and can actually halt the development of software. Now, how we can address technical debt is basically by doing refactoring. Okay. Now, what happens is that researchers have found that in many cases, refactoring is being postponed. First of all, due to constraints related to budget or to time, and in other cases, because end users of the system cannot directly witness technical debt. So the next question is, how do we measure technical debt? And this was very important in our context because we wanted to compare technical debt between applications and between different versions of the same application. So there are several tools that can measure technical debt and which provide a quantitative measure, which is very important for us in our case study. Now, most of these tools, what they do is they employ static code analysis, they employ software metrics, and they basically check the values of these metrics against a set of predefined rules. And when the rules are broken, these tools, they generate issues. Okay, so it's showing that developers have to fix this or they have to fix that. Now, of course, that as in many cases, using tools also has both strengths and it also has weaknesses. Now, the most important strength and the reason why we use tooling is that tools provide a quantitative evaluation of existing issues. So basically, they provide a number-driven model, okay, which allows us to compare the level of technical debt across systems and across system versions, okay? In another idea is that since they provide a quantitative evaluation, previous research has shown that it allows better control over software quality, and it allows teams to time refactoring efforts. Also, it has a psychological component because solving technical debt and eliminating it basically was shown to boost developer morale. Now, with regards to weaknesses, one inconsistent weakness is that different quality models report technical debt differently. So basically, we're going to find different levels of technical debt reported by different tools, depending on how they perceive it and depending on what they use behind the scenes. Another important observation is that of all the rules and that are used to generate and to characterize technical debt, very recent research has shown that there's only a small subset which actually leads to documented software defects, which means that sometimes these quantitative models might not be that accurate. Okay. So in light of this, we set up our research objective to investigate three things. So how much technical debt we have in software, so its presence, what is its makeup, so characteristics, what is the composition of technical debt, and of course, how long it evolves. So basically, for how long can we find technical debt items inside software? How quick are developers into reacting and to solving this technical debt? And to study this, we've selected 3 open source applications. Now, the main driver of selecting open source applications was actually the fact that we wanted to have free access to source code and we wanted to have free access to all the versions of the source code. So we selected 3 well-known applications written using the Java platform, and we ended up with 110 versions in our case study, okay, which were more or less equally split between gedit, FreeMind, and TachGuitar. So here you can see the first and the last version of each application. That in case of FreeMind, we've covered around 15 years of development, and the same large time span is evidenced also in gedit and for TachGuitar over 10 years, up almost 20 years of development time. And we can see that we have a lot of technical debt to work with. Okay, so we have tens of workdays of technical debt made up of tens of thousands of issues, okay, over which we can go and which we can study. So what we did is we made sure to manually examine each version source code. We then imported each version into the latest version of Sonar Cube, and this resulted in over 50,000 issues. And every data point that we collected, we also made available in a replication package to make sure that our study can be replicated or that it can be extended. So let's go quickly over our main results. So this is basically the technical depth that we see in FreeMind. So here on the horizontal axis, you see the FreeMind versions. And on the vertical axis, you see either the size of the application shown by this dotted line, or you see the amount of technical depth that is present. So the amount of technical depth is shown by the hashed line, where the darker hash shows the amount of technical depth that was introduced during that version. So for instance, FreeMind 080 is remarkable because here we notice a large swath of technical depth being introduced, which then we see that is being resolved 2 versions later. So in order to answer the first research question, we did the same thing for JEdit and for TAF-Guitar. But here we notice that while the application size increases slowly over the versions, we kind of notice a stagnation or even a slow decrease in the amount of technical depth, which to us signals the fact that the code that was introduced in later versions of these applications was introduced by developers who were either experienced, generically speaking, or were already familiar with the context of these applications and their architecture. So, for instance, this is how we answer research question 1. So we observe how technical depth is introduced and where technical depth and the versions in which technical depth is eliminated from applications. Now, the second question is basically what makes up this technical depth. Okay, and here we find that across all 3 applications, most of technical depth is made up by what SonarCube labels as code smells. Okay, so these are basically deficiencies in code which usually make development more difficult, make program understanding more difficult, and so on. But of course, we know that this isn't something that is 100% accurate. We find that bugs and bugs and vulnerabilities, we find them to be much lesser represented. Now, regarding the composition, we find that most of it is basically labeled as being critical or as being major in importance. And last but not least, what we were able to do is we were able to draw a number of 9 rules from SonarCube, with which generate over half all the technical depth that are found in each of these applications. And this is something that we found to be remarkable. And the next step for us is to figure out how these rules actually translate into real-life software defects. And finally, what we did, and this is the last slide of the presentation, is how quickly these technical depth issues are being resolved. And we basically found no correlation in the severity of an issue or the type of an issue and its lifetime. So it shows that developers don't prioritize issues according to severity or according to type when they fix them. Okay, and basically the next step for us is to figure out how these issues translate into real life issues in software and real life software defects. Okay, thank you. This was all.
Thank you, Arthur, for the presentation. Very interesting study. Let's see. While we wait for questions to come in, let me start with one very speculative question. What do you think about your results translating to more traditional industry closed source projects? Do you think that you will find similar patterns, or do you expect in companies to find something dramatically different from what you encounter, particularly in terms of evolution and prioritization? Which one sort of the
That's very interesting question, and actually we are considering in continuing our work and trying to find some industrial systems where we have access to source code. However, as documentation for this article, we did look at previous research which examines industrial systems, and we did find that these levels of technical depth to be quite representative. So we don't expect let's say wildly different changes. What we have observed, however, is that in each system, basically it's early versions, you know, when they start developing the system and there's the initial push to get out the minimum viable product, if you will, then there we have wild swings in technical depth because the architecture changes, perhaps the developers change, the libraries and frameworks that are being used sometimes are swapped out, and that leads to a lot of large-scale changes.
Okay. All right. We don't have any questions from the audience yet. So let me ask another question. You just pointed to something interesting. The impact of major re-architecturings on the amount of technical debt. As a practitioner, I noticed that in different companies and industries, there's a periodic major re-architectures, and some companies tend to sort of start from zero versus evolving their existing system. Do you think that would produce a significant variance in terms of the number of technical debt introduced in the system, or how the technical debt evolves, those different approaches?
I think we've come over a study that actually examines this in industry systems, and what they found was that in cases where technical debt was not actually and proactively accounted for, the accumulation of technical debt led to what they called crisis in development, where basically everything had to be stopped for a month or two and the entire solution had to be refactored. And during that time, it was very painful because developers couldn't work on new functionality. And of course, from the end user's perspective, nothing new or no valuable functionalities were coming out for them to use. Okay.
All right. Thank you. Thanks for the answers. We're now moving to the next paper. This is the first of the two papers from the emerging results and vision track. The first paper is being presented by Valentina Lenarduzzi. How long do junior developers take to remove technical debt? Valentina, the floor is yours.
Hello, can you hear me? Yeah, perfect. Can you see my screen now? Okay, so good morning, everyone. I am Valentina Lenarduzzi from LUT University, and today during my presentation, I will be showing you our work related to how long the junior developers take to remove the technical debt items. This work was done in collaboration with the University of Novi Sad in Serbia and University of Tampere University in Finland. In the presentation today, we'll be showing you the problem and the motivation because we decide to conduct this work, the case study design that we adopted and we designed, and there is the results and the conclusion of this work. Technical debt items, and now is not anymore the necessity to explain again what is technical debt because the other two presenters already explained the simple context of what is technical debt. But we know the technical debt items are detected by many static automatic analysis tools, and they are based on different rules. However, we know, based on some results, some papers published before, then developers do not rely about their rule usefulness. So we come in our mind the idea to investigate if the lower usefulness perception of the developer is based on the experience. What I mean, Experienced developer trust only in their skill, judgment, and they don't want to rely on the awareness provided by the tool because they consider they're really expert. And so we decided to ask about the junior developers, what they think about and what they how they manage the technical debt. So the goal of this paper is to understand how long junior developers take to fix technical debt item. And we conceptualize 4 research questions. The first one is related to the type and how many technical debt items are introduced by the junior developers. The second research question is related how the common refactor, which kind of technical debt item the junior developers commonly refactor, how long they spend to refactor these items, and which is the remediation time accuracy according to the estimated time by the tool. We designed a multiple case study with the replication design, one in Tampere University, replication 1, and the second in the University of Novi Sad, replication 2. And we identified a population of 585 for years graduated and master students. And we select the student with a comparable background and programming experience comparable to each other. This is the context of our study: 2 replication each university, 3 months for both duration, 130% participant in replication 1 and 52 in replication 2, 26 and 7 groups. The project assignment was develop a real product, and the refactoring task was that the student should resolve as many issues as possible detected by SonarQube. Just a clarification why we use SonarQube. We use SonarQube first because it's the most adopted technical debt tools. Second, because 2 of the authors, me and Davide Taibi, have an experience with this tool. And then, since the model of SonarQube calculate the technical debt only based on square index, and so based on one type of violation, we collected the information of the technical debt and the 2 remediation efforts that are assigned to the other 2 types of violation that you can violate in your code. The data collection was to, of course, then collect the TD items detected by the tool, COSMELF, bug and vulnerability. Please have a look that COSMELF by SonarQube are not the COSMEL defined by Martin Fowler, but other types of COSMELs. The status of the issues, the 3 types of effort, and the actual effort to fix the issues. Other information are collected at commit level. Regarding the data analysis, we calculate the relative error, the mean magnitude relative error, and the median magnitude relative error. The results that we achieve are mainly promising because for the first research question, we discovered that the vast majority of the items introduced are COSMELs at the maximum 90% in replication 1, and their factor type are according to the first results, so are mainly COSMELs with the 100% of refactor in replication 2. We discovered that the refactoring prioritization provided by the junior developers are not according by severity and type assigned by SonarQube, but they decide to refactor based on their perception of criticality and based on when the first item was introduced in the code. And if we compare with the actual effort calculated by the tool, we discovered that the student spend less than 50% of the estimated one, and in certain cases are 20 times lower than the estimated. In conclusion, we discovered that junior developers focus homogeneously on different types of technical debt items, never spending more than 50% of the time estimated by SonarQube. This means that to confirm the results that the model of SonarQube should be carefully customized by the company, and also connecting to the first question of the first presentation, it could be better than during the education program, universities start to teach using automatic static analysis tools and introduce technical debt as concept on their program. Thank you very much for your attention. I am ready for questions.
Thank you, Valentina, for the presentation. While we wait for questions to come in, let me start with one. I was curious if you have any insights in terms of what drove the difference in numbers of code smells across the two replications. I noticed in the paper that one had an order of magnitude 10x more code smells in replication 1 relative to replication 2. And I was wondering if you have some sort of insights on why that might have been the case.
Why do you mean that? Why there is a different percentage of code smell introduced in the code among the two presentations? Sorry, the two replications.
Yeah, why one has like a 4,000 plus code smells and the other one 400? Was it something about the projects the students work on, the technical aspects of it, or something?
You have to consider that the students should develop the same product, all the 26 group, for example,
okay.
And maybe was the decision of the skills, the quality skills of the developer when they develop the code, of course, because you have to consider that they have comparable skills because they have the same background and the same experience in previous coding. But of course, there is the human factor that can affect how much qualitatively could be your code.
Okay.
So maybe is this one of the reasons, because all the students should perform mandatory courses before attending, even the course in Tampere and a course in Novi Sad.
Okay, thank you. We've noticed a little bit of the delay in the questions coming in, so we may have to answer some additional questions on the comments later, just so you're aware.
Okay.
All right. Thank you for the presentation, and now we move.
Thank you very much.
To the last talk of the day by Zadia, Codabux.
Hi.
She's going to be presenting another of the papers on the emerging results and vision paper track entitled Profiling Developers Through the Lens of Technical Debt. Zadia, the floor is yours.
Hi, can you hear me? Hello? Hello?
Yes, we can hear you.
Oh, good. Hello, my name is Zadia Codabux. This study, Profiling Developers Through the Lens of Technical Debt, is in collaboration with my colleague and co-author, Dutchyn. The motivation behind this study is to understand developers and how their capabilities and maturity are important to managing technical debt. The differences of the level of maturity and capabilities will show during the data analysis. So very quickly, technical debt is a metaphor for poor design choices and shortcuts made during software development for short-term benefits that can be detrimental in the long term if not properly managed. We use the publicly available technical debt dataset as a sample of developers' activities in open source projects. The technical debt dataset captures and categorizes developer activities. Based on our motivation, we came up with this research question: what do developers' activities regarding inducing and refactoring code smells and bad practices tell us about their technical debt management? By developers' activities, we mean commit actions, violations, both smells and bad practices they introduce, and the type of refactoring they undertake. So code smell is a term coined by Ken Beck and popularized in Martin Fowler's refactoring book of potential design weaknesses in the source code. Next, let's have a look at the data set. So the technical debt data set is a curated data set of Apache projects. For each project, we have authorships and commits from GitHub, faults extracted using the SZZ algorithm, issues from the Jira defect tracking system, refactoring types characterized by refactoring minor, and violations from SonarQube. For information, authorships are changes to the code, and commits are accepted changes into the main branch. We picked one of the largest projects in the dataset, Apache Beam, over a period of 5 years. It has about more than 22,000 authorships and commits, more than 10,000 refactoring actions, and more than 10,000 technical debt items. The tables that we used are shown in red in the diagram, and the summary statistics we computed are in blue, namely the count of commits and authorships, the count refactorings, and the count code smell, bad practice creations, and closes. Next, let's have a look at the results. So this graph shows the distribution of authorships in blue and committers in orange. We found that most committers are authors, and overcommitters stand out as blips, where the orange commit line jumps above or below the blue author count line. A few stand out. So the green stars represent developers who committed a large number of other authors' work. For example, these might be suggestive of people who have an oversight of the project. The red star is an automated person, for instance, a bot, which was excluded in the analysis. Lastly, the top 23 handles represent 63% of all authorships and 70% of all commits to the main branch. Next, we look at the violations in terms of code smells and bad practices by author. Note that the total number of commits is normalized to 100% in this graph, and each vertical bar represents a single author. We found that only 3 code smell out of the 12 distinct in bright orange showed substantial differences across the developers. These are long method, dead code, and complex method. We merged the other 9 code smell into dim orange. For the bad practices, only 8 bad practices out of 37 distinct showed up more than 1% of the time. The other 26 represents less than 1% of the violations. We also noticed that only 3 developers engaged in move file in yellow, and 1 developer was more prominent than the other 2. Lastly, abstraction violations represented 25% of all violations in dark green, followed by obsolete code and magic numbers. Next, we look at refactoring by author. We found that 6 developers contribute to most of the refactorings, and other 2 follow closely among the 23 distinct developers. We have 16 distinct refactoring types. 2 authors performed 1 refactoring type exclusively, inline method in dark blue and pushdown method in red. And except for these 2, everyone else employed extract method in yellow, a relatively sophisticated refactoring type. Move class in green was a common refactoring for most other authors, and in some cases, a substantial majority of their actions. Only 5 authors employed a move method in dark orange, but they used it quite extensively, accounting for 25% or more of their refactoring activities. Based on these results, we observe different roles. So the probable architects are the one moving code around and across packages. Quality assurance people are the one creating and closing large number of items. Code reviewers are the ones committing other people's authorship and changes. Next, the actions performed suggested differences in code knowledge. So some perform complex refactoring, for instance, instantiating superclasses and moving methods up and down the hierarchy. Others perform a simple refactoring. For example, they mostly moved files around. Lastly, different coding maturity. So immature developers showed by having a large number of abstraction violations or complex code or magic number violations. And mature developers undertook a more abstract code motion. For instance, generalization by pushing method up and down. And they also seem to tolerate more code smell. So to summarize, in this study, we performed the act of profiling, not creating profiles, using commit, refactoring, and violations to recognize developers' similarities and differences, especially with respect to their level of coding maturity and coding specialization. Some of the future research avenues will be to include more projects, include more characteristics of the data, for instance, the JIRA issues, perform a time series analysis to analyze developers' maturity over time, include other GitHub branches in addition to the main. All this so that we can accomplish the ultimate goal of creating developer profiles with respect to how they induce and manage technical debt. Thank you for your attention. These are our contact details as well as the link to the replication package. We are open to questions.
Thank you, Zadia, for the presentation. Both authors are here to answer questions. While we wait for the questions to come in, let me start with one. I was wondering if you can elaborate a little bit more on why this particular project was selected. You pointed out as being one of the largest. Was sort of that the only criteria, or was it something else that sort of drove the selection? And how do you think that would impact the results? Hello, can you hear us?
Hello.
Yeah.
So we selected the BEAM project after looking at a number of the other projects. The technical debt data set comprises primarily of the Apache project. We selected it partly because of the length of time that it has been in progress. So we had a considerable amount of data, both over time and number of commits. Some of the projects were considerably smaller. There were other candidates that we considered as well, but for the purposes of trying to keep our graphs to an understandable size, we chose one. Okay, perfect. Thanks. Let me show. I have one question from Simona. It was not clear for her if the people who wrote the code are the same, the ones that made the refactoring. One of the points she brings up is understanding someone else's code can add level of complexity and consequently doing or not the work. Absolutely. The original version of the paper did actually include the author names themselves as originally in the public domain data. So as a result, we could have clearly connected them. But now with the requirements for anonymization, it's less clear. The answer to the question is some of them who did the refactorings were also the authors, and some of them were not. And it would be interesting actually to delve deeper into those connections. The difficulty that we run into is that the more connections we draw, the less de-anonymized the data is. Okay. And there's a trade-off there. Okay, thank you. All right, thank you for the presentation, for answering the questions. Thank you everyone for being part of the technical debt session, and this is the end of it. Thank you.